Hey, good morning, everybody. Welcome to the webinar. My name is David Simpson. Today we're talking about relative page numbering, a feature of DB2 12 for ZOS. So this webinar is a pretty concise topic and probably will be a little bit shorter than a lot of the webinars we do. So thank you for joining us today. Again, my name is David Simpson. My email address is on the board there, and you can feel free to use that to interact with me. It's probably better to use that than to reply to the email that invited you to the webinar or the one that you used to sign up. It's a great way to find me, and you can also follow us on Twitter down at the bottom there, at Themis Training. So thanks for joining us today, and hope you get something out of this. This material comes from our version 12 transition class, and down at the bottom of this page, if you go download the slides, you'll be able to find, click on that link to register if you want to take a look at the outline and register for upcoming classes. Also, right above that, themisinc.com/webinars, you will find links to all of our past webinars, registration for upcoming webinars, and also if you would like to download the slide deck for today's webinar, you can go to that link right now, and toward the top of the screen will be this webinar and a button you can push to grab these slides for your own use. So that'll also make it easier to click on the link at the bottom if you'd like to see information about the class that this comes from. All right, so just a quick word from our sponsor. I work for Themis. We do corporate training and consulting, and I specialize in databases and in DB2 in particular. So I spend most of my weeks working with clients, trying to help them be better with things like DB2. So one of the classes I've been teaching an awful lot lately is this DB2 12 transition for administrators. So that's kind of what I do. We can come to you if you have a big enough group, or we do a lot of public enrollment training. Most of that is virtual now, and again, on our website you can see lists of all of that stuff. So that's us. This is me. This is in the deck if you want to read more about me. A couple places where you can find me. I mentioned on Twitter, I'm at ThemisDave. You can see past webinars that I've done at themisinc.com/webinars. And I also contribute to the iDoug content blog. So if there's a link there at the bottom of the screen for that as well. iDoug.org/content. That committee puts out new material just about every week. There's a new article going out there, all DB2 related stuff. And if you scroll around long enough in there, you'll find some of my stuff there as well. So all kinds of places to find me. And if you have questions or comments, feel free to email me. I don't mind that interaction at all. So today, we're going to talk a little bit about new partitioning options on DB2 12. A couple months ago, I did a webinar on just more partitioning in general, and you can find that playback out there on the site as well. But today we're going to be looking at a particular option or a particular feature of range partitioning as it relates to DB2 12, and that's called relative page numbering. So we'll take a little bit of a review of partitioning choices. We'll talk about how absolute page numbering works. That's the way things have always worked until now. And then compare and contrast that with relative page numbering on DB2 12. So the evolution of partitioning. Back in the old days, we just called it partitioning because there was only one way to do things. The pre-version 8 way to do partitioning is now called index-controlled range partitioning. It is deprecated, meaning that they prefer we not do that anymore. Any objects that you created ages ago using that method are still there and they still work just fine. We can migrate without too much trouble, at least one step forward, and with a little bit more trouble all the way to the more current kinds of table spaces. You can still create index-controlled range partition table spaces even on version 12, although there is a zparm you can set to disallow that so that we don't accidentally create deprecated kinds of objects. And by deprecated, I think IBM just means they would prefer you not do it, or it's going, but not quite gone yet. Version 8 implemented table-controlled range partitioning. That's just where we move the limit keys from an index to a table. And that is also deprecated if you haven't combined it with the universal table spaces that began in version 9. So in version 9, we have the advent of the universal table space. That's just kind of fancy words for, well, in the case of range partitioning, universal partition by range is similar to the kind of partitioning we've been doing all along. It must be table controlled, in other words, limit keys defined at the table level rather than the index level. But it really just combines the benefits of partitioning and segmentation. And that's the main thing that happened. You now have a partitioned segmented table space. And when you do that, IBM calls it universal partition by range. We can migrate from a table-controlled range partition table space to a universal partition by range. However, that involves one of those deferred pending changes that was discussed in the January webinar. The downside to that is you do have to be able to reorg the entire partition table space in one step. You can't do it at the partition level, which makes it problematic, especially if you have non-partition indexes. Right. So universal partition by range is kind of the the next step forward in the in the same scheme of partitioning that we've been using since the beginning. Version 9 also implemented this thing called universal partition by growth, which is a whole nother animal that has its own challenges. I have a link there at the bottom to a recent article on the iDoug content site that treats pretty thoroughly the challenges and joys of dealing with universal partition by growth. So that's an article by Julia Carter that was published pretty recently on the iDoug Beginners blog. And I encourage you to check that out if you haven't thought through the challenges of universal partition by growth yet. It covered pretty solidly there. In version 12, we take a step forward, and we're going to be talking only universal partition by range here. Right, so this is the only type of table space that relative page numbering will apply to or can apply to. Universal partition by range, and our choices now are page numbering absolute or page numbering relative. Absolute page numbering is, again, just new terminology for the thing that we've always done. So page numbers across partitions of a partition table space are never duplicated in the current scheme. So the page numbering scheme is such that you'll never find the same page number in two different partitions. And we'll see exactly how that works in just a minute. In kind of researching this feature when version 12 was new, I learned a lot that I had never known before about the way page numbering worked in conjunction with partitioning prior to version 12. Okay, so we have those two choices now, absolute page numbering or relative page numbering. All right, so relative page numbering just means that every partition of a partitioned table space will start numbering its pages with 0 again. Right? So, part number 1 starts at page 0 and goes forward, and part number 2 also has a page 0 and goes forward. So, pages can be duplicated and will be duplicated across different partitions. So I guess another way of saying that is, knowing a page number doesn't tell you the precise location of that page, because we also need to know the partition number that it goes in. But what this does is it blows the lid off of the maximum size of a table space. We don't have to reserve page numbers for all of the parts now, because each one starts over. And I think you see the limitations there now. That the DS size per partition is now 1 terabyte, right? And that requires relative page numbering. But if you can get up to 4,096 partitions with each one having a DS size of 1 terabyte, if you add all that up, that adds up to about 4 petabytes as the largest theoretical size for a table. And at least theoretically, if every page has maxed out its number of rows, you get to 256 trillion rows, theoretically, in a single table using relative page numbering. Clearly, the indexes are going to have to change, right? So a RID, if you're using relative page numbering, now has to have a 2-byte part number attached to it, right? So a partition number has to be glued on to the beginning of the RID so that we know which partition we're talking about. So when you're using relative page numbering, this is part of the price you pay is 2 bytes extra in the RID. So we have a 2-byte part number, a 4-byte page number, and a 1-byte row number. And I think if you add that up, that's 7 bytes for the RID. Okay. Utilities and log also had to be modified for this. And another quick note, you do have to be, I guess I'll call it version 12 new function mode. The new terminology for that is, version 12 release 1 M500 or above in order for this to work. Another quick note that is always true when you're using a new feature, you want to make sure that any third-party tools or utilities that you have are going to support this before you try and use it. I learned that lesson the hard way as a DBA years ago. I think it was version 8 when they increased the maximum size of a table name, length of a table name. I accidentally created a 19-character table name, and none of my tools could deal with it because they hadn't yet been updated to allow for larger table names. So, same thing here, right? Because the indexes and the log and the physical structure of your table space are changing, if you're using log analysis tools or third-party utilities that are doing loads or reorgs or whatever of these things, you do want to make sure that your tools will back you up in this and that you're at current levels of the tools that will support this new functionality. So that's like any new feature that you use. You want to make sure that your tools will support you. Okay. So I think we're going to take a look at some examples of this, and I actually went and did some DSN1 prints on some of these objects so that we can see exactly what they look like. So the create table space insert algorithm is another new feature that we're not going to talk about here, although if you look for John Campbell's presentations on this from IBM, he has quite a bit to say about it. Page numbering, absolute or relative. Okay, again, absolute is the old way, the way we've always done it, and relative is the new thing. It's only an option on universal partition by range. Your DS size can be now between 1 gig and a terabyte, 1024 gig. And when you are relative page numbering, you can do DS size at the partition level, which is pretty dang cool. So let's talk about the niche for just a second. Who's going to use this? Who's going to use relative page numbering? Well, number one, if you want a really, really large table, right? So if you want to blow the old 16 terabyte limitation on a table and the size of a table, you need relative page numbering. But you could also make use of this even if you're not close to that limit, but you do have partitions in a table space that are getting quite large. Right? So maybe a single partition is close to your DS size, and you would like to be able to let that partition grow without doing rebalancing or adding of partitions in the middle or anything like that. By the way, version 12 also allows you to do additions of partitions in the middle of a table space, which might also be helpful. That's another feature that we're not going to talk about today, but might be useful in the similar situation. So let's say your DS size is at 64 gig, and you have a single partition in the middle of your table space that's approaching that. You're going to have to do one of a few things, right? You're going to have to either rebalance your partitions. You're going to have to add new partitions in the middle if you're version 12. You're going to have to increase the DS size of the entire table space. Or another option here is to go to relative page numbering, and then you can increase the size of just the partition that is causing the problem. Right? So one of the side effects or side benefits of relative page numbering is that the DS size can now be done at the partition level, and also altering the DS size after your relative page numbering is no longer a pending change, it's an immediate change. It does not require a reorg after you get to relative page numbering. Right? We'll come back to that in a minute. So here's the chart, comes straight out of the SQL reference guide, that gives you the rules for how many partitions you're allowed to have when you have a certain page size and a certain DS size. This chart's been around for a long time. It changes, from one release to the next. Really, I guess the last time it changed in any significant way was probably version 8 when they, so it changes when they went to 4,096 partitions, right? So you can theoretically have 4,096 partitions, but if you're in a 4K page, if you look down the left column there for the 4K page size, yeah, we can have 4,096 partitions, but if your dataset size, your DS size goes bigger than 4 gig, then the number starts going down, right? So at 8 gig DS size, I can only have 2,048 partitions, and for 32 gig DS size, I can only have 512. And if you get down to the largest DS size allowed in version 11, 256 gig, I can only have 64 partitions, which goes back to a limit from like DB2 version 5 or so, right? That used to be the maximum number of partitions. We can mitigate that somewhat by increasing the page size. So for an 8K page, those numbers basically double. And for a 16K page, they basically double again. Right? So you're always balancing these three things against each other for really large table spaces: your DS size and the page size and the maximum number of partitions that you're allowed. Okay. By the way, this chart all assumes that you're using a 5-byte RID, or what we used to call a large table space, and that you're using SMS managed storage with vSAM extended addressability enabled. All right, so your numbers are actually a lot lower than this if those two things aren't true. Okay. So I guess we'll say any kind of modern table partitioning, post version 6 or 7. Okay. What I never really understood until more recently is why this chart is the way it is. So I'm going to go through an example here. We create a table space, page num absolute, so that's the old kind. The call out there mentions that the default for this is controlled by a zparm called page set page num. I guess I would probably recommend leaving that at absolute when you go to version 12 so that you don't accidentally create things in a way that you weren't expecting. And we'll see the side effects of being relative page numbering in a minute. All right, I'm in a 4K buffer pool, got a DS size of 1 gig and only 4 partitions. Okay. And I went out and loaded some data into this and then went and did a DSN1 print. DSN1 print's a great little standalone or service aid that will tell you, basically does a formatted dump of what's in an underlying VSAM object. And so the one I printed here was partition 2 of this table space. And I went and looked at the first page in partition 2. And you see the page number. And I'll follow this up by saying I only loaded a handful of rows into this thing, into each part. So, so the data in page 1 only took up maybe 2 or 3 data pages, just a handful of data. But you see the first page number in part 2 is 40,000. All right, now this is hex, so we have to do a little math to see, how many page numbers we just wasted. So I actually got out my Windows calculator, which has a programmer mode now, which I really like. And I put in the number 40,000 and it said, okay, if you're speaking in base 10, that's 262,144. So the first page in part 2 is really page 262,144. Over on the right, I did some math. I said, okay, well, if each one of those pages is 4K, multiply that number by 4, you get 1,048,576K, which is 1 gig. What does that correspond to? If we go back a couple of slides, that corresponds to the DS size that I chose up here, is 1 gig. So each partition reserves for itself 1 gigabyte worth of page numbers. Right? 1 gigabyte worth of page numbers. If I had said the DS size was 4 gig, then you would have seen that that first page number of part 2 would be even bigger, about 4 times that. So even though I only have 10 rows in the first partition, it kind of reserved 250,000 page numbers because I got 4K pages that are, and I have to allow for 1 gig worth of data in that part. So this is how absolute page numbering works. Every partition reserves for itself. It doesn't allocate all these pages, but it reserves the page numbers for enough pages to meet your DS size. That's absolute page numbering. So partition 3, the first page number would be something like 80,000 here, which again is reserving another gigabyte worth of page numbers. That's absolute page numbering. Okay. And I think these bullet points are saying, what I just said. The second one there basically says, if you give DB2 a RID, which includes the page number, it's able to do math and figure out which partition that RID belongs in, right? Or which partition to go to find that RID. You give it a page number, DB2 looks at the DS size and can do a little bit of math to figure out what part we're talking about. Again, absolute page number. The page number is not physically stored in the RID, but it can be derived. The partition number, excuse me, is not stored in the RID, but it can be derived by looking at the DS size and doing some math. Okay. And if you alter the DS size, this is something else I didn't understand until more recently. Altering the DS size prior to version 12 with relative page numbering requires a deferred change and it requires a reorg of the entire table space because you just blew the page numbering scheme out of the water. You have to go, it has to go renumber everything. Right? So it has to reserve more pages in each partition. So that is why in an absolute page numbering scheme, you have to reorg the table space in order to change the DS size. All right, so here I did an alter. Let's take that thing and change it to relative page numbering. And then I went and did my DSN1 print on the second partition again. and the first page is page 0. Okay, so every partition starts its page number over with 0 now. What that does mean, so this gives you, basically the limits that I had at the table space level before now apply to each partition. And each partition can be up to 1 terabyte. We have enough page numbers to address a terabyte of data in each partition now, if you set your DS size that way. So what does this do to me, otherwise? Well, once you are relative page numbering, and actually let's go back. Notice at the top there, when I did that alter, it put me into advisor reorg pending. This means this is a pending change. The reorg that I do to accomplish this change will have to be the entire table space. So I don't want to make it sound too easy here. To get from absolute page numbering to relative page numbering, you will need to reorg the entire table space. And again, especially since the target market for this is going to be really large things, that can be a real challenge. Some of your third-party utilities will help you get there more quickly, but this could be a significant challenge to get it done. Okay. Once you're there, though, DS size can be altered at the partition level, and altering DS size becomes an immediate change, not a deferred change anymore. You don't require a reorg, right? Because each of the partitions operate independently of each other for their page numbering schemes. When you do that alter, it does still invalidate packages. I'm not really sure why that's necessary, but apparently it is. This is an annoyance to a lot of the clients I work with, that say, hey, this is an immediate change. It's supposedly no outage. But if I do the change and 2,000 packages get invalidated, that's not really quite an online change. So it does still invalidate packages, which is annoying, but that's less of an issue than having to do that reorg at the table space level. Once you do this, your max DS size is 1 terabyte, and your maximum theoretical table size anyway is 4 petabytes or 256 trillion rows. Okay. It eliminates all those limitations that we saw in the chart a few slides ago. Right? Your DS size and your page size and your number of partitions, none of those are related to each other anymore. Again, because we've got a ridiculous number of addressable pages. Okay. We should talk for a minute about indexes. And so the big thing, the big price you're going to pay for this is that the RID is going to go from 5 bytes to 7. And that's just straight up, we need to include the partition number in the RID now. Because the page number doesn't tell us which partition it's in anymore, we have to tag 2 extra bytes onto the RID, and it's just the straight up partition number. Okay. Index header records get a little bit bigger. The max partition size for an index is now also a terabyte, and the DS size keyword can actually be specified on a partitioned index now. So it used to be the DS size of the index and table space were kind of related to each other, and now they can be independent of each other. There are still some defaults that you should take into account, but you can work those things independently of each other. Right? And there's catalog support for this in sysindexes and sysindexpart. For an NPI, same thing, 7-byte RID, where it keeps the partition number. That one, the page numbering scheme always represents absolute. Okay. Here I went out and did a DSN1 print of a partitioned index. I actually just did this morning in preparation for this. Parsed out the way the RID is stored in the index. So up top there, you see, a particular key that was indexed, and it shows you the hex, right? Charlie 4, Fox 1, Fox 1, and then the RIDs that value has associated with it. And if you count out the bytes there, you see 8 bytes for the RID. Now I just told you 7 bytes is what's needed, right, for the RID, and those are actually the 7 bytes to the right. The leftmost byte is for the pseudo deleted flag. And actually I zoomed in on one of the RIDs there that is actually pseudo deleted. In other words, that row is deleted. And you see the leftmost byte marks it as deleted. The next 2 bytes are the partition number. So these are in partition 2 actually, which in hex is 1, right? Because there's a 0. The next 4 bytes are the page number, and the final byte is the row number on the page. So this is the way the indexes are laid out now, with the 7-byte RID instead of the previous 5-byte RID. And you got the extra byte to the left for pseudo deletes. Okay. So that's a quick overview of the relative page numbering. Again, I think the 2 niches for it are going to be when you have table spaces that are growing quite large, when you add up the whole table space, or even where you have table spaces where the whole thing isn't pushing any limits, but you have individual partitions that are pushing their DS size limit, and you would like to not have to think about redistributing or adding partitions. Relative page numbering will allow you to alter the DS size of those parts without reference to any other parts, and also to do it without reorging the entire table space every time you do it. Okay. So that is what I got for you today. Again, as I said before, you can feel free to email me with questions or comments. You can find me on Twitter at ThemisDave, or my company at Themis Training. Thanks for being here today, and hope to see you in a class where we can talk about this and other version 12 features in the near future. Thanks, and have a great rest of your day.